Hello everyone, I am Siv Prakash, Research Scholar, Department of Electrical Engineering, IIT Beach. This is the ninth session, which is related to the cooling device, like a Peltier device. Peltier is the device to cool the component surface of the component, which is placed between the heat sink and surface of the component. Because of the very component have a limitation of the temperature, you can't be work beyond this limitation of the temperature any devices, so that it will require to cool the element. Like if you talk about the switches have a very common devices we use which used, and it will be heat up because of the switching losses and conduction losses. There are a lot of switches to cool this one. It will be many type of system, like for the only heat sink, or for the cooling system is for using of the fan. And it will be more required, if you have more required, then you can use the Peltier device also. Peltier device have a required some external supply to cool this one. Like it will work a bit like a heat pump, transfer from the lower temperature to the higher temperature. So this was the temperature as T1, and this will be cold mm, the lower temperature of this one, and another is hot temperature at a high temperature of the cold. This is a T2 to transfer a heat from cold to hot temperature, or to minimum to maximum temperature. To heat transfer, it will use a pump, heat pump. It is known as a heat pump. The device is known as the Peltier device. It is placed between this one, because in normal condition heat will transfer from higher temperature to the lower temperature, but here the component is placed here, and component will be heat up. When this will be heat up, then temperature transfer from here to here, like that. This is a Peltier device. It will require some supply of voltage, some supply of electrical supply. We can give from a voltage source like the battery or PV system also. For the PV system, you should apply a DC-DC converter before the PV system, PV panel. This is the voltage of VT, terminal voltage of solar panel. This is the power requirement of the Peltier device, VP, and current of IP. This is DC-DC converter controlled from the duty cycle D. It is used for the maximum power point tracking point. You can track the maximum power also. This is the Q. C is the power which will transfer from lower to higher temperature. You can denote in wattage also, because this one is the heat transfer, the heat rate, energy per second is the watt, the joule per second also. 1 watt is equal to 1 joules. 1 watt second is equal to 1 joule per second. So cold, this one is the hot temperature. This is the electrical supply, BP, then you can say that hot temperature is the cold temperature plus of the electrical supply which is applied. the devices. It is placed between the heatsink and the devices element to control the thermal resistance. Okay, now start the question. The specification of a electric Peltier module from a data sheet is shown below. A 20-volt battery is connected to this thermoelectric Peltier module via a series resistance Rs. Here is clearly shown. As shown in the figure below, what is the has the theoretical value of resistance Rs such that it will satisfy all the parameters rating of the given specification. You have a two condition for the 20 degree centigrade and 50 degree centigrade. But important thing is the which one you select, or 25 degree centigrade or 50 degree centigrade. This is the hot temperature, hot sides temperature. This is the device rating. But also important thing is the delta and Q max power. How much power it will deliver from lower temperature to the higher temperature. It will be 50 to 57 only. Sorry. Suppose you select the 57 or higher power transfer. Then you should use of this one voltage and current. This is the VP voltage here, and this is the IP current. Then you can simply calculate the RS because of this one. If you apply the KVL here, this is a 20 volt is equal to IP into RS plus of VP. To calculate RS, it will be 20 minus VP divided by of IP. Where the VP IP value is two values. This IP is the same, but voltage has two value 14.4 and 16.4. 14.4 for the 50 watts and 16.4 for the 57 watt. Suppose you can you select the 57. Q max is equal to 57. Here looks here. If you select this one, Q is 57. But this is a depending. This is the depend on the material of the all of the thing. It will be not in your hand to supply the power at least at this, but when it will be 57 is the maximum, it will be transfer maximum watt, but it will not transfer at all time. It have some transfer the 50 to 57. Suppose you select as the 57, but it will transfer only 50 watt in any condition. At any condition, it will supply a 50 watt only. But if you calculate it at 57 watt, you will find the VP is the given as the 16.4 volt and the IP is 6.4 volt, 6.4 ampere. This is the sum power. PP you can say as VP into IP. This power is related to only when to transfer the 57 watt. But if any condition, this will continuously supply the power because of the our voltage is connected to 20 volt and resistance. Current will be fixed. That's why BP will be fixed because of the resistance is fixed and voltage supply is 20 volt. And this much power is continuously supplied through the Peltier device. But suppose this will only for this is for the 57 watt, but it will not transfer exactly 57 watt of temperature of energy to the a higher temperature. Then what happened? It will transfer looks like a 50 watt only, but it have a same power supply we given. The remaining power is losses through this one resistance, module resistance. It will be module resistance also given here. The remaining power drop here, and the pelleted device will be heat up because of the supply given supply is more to the transfer supply, but transfer is not sufficient as the 57 was like 57 watt. In that condition, the extra amount of energy will be dissipated through the resistance of the module resistance. That's why you should take as a resistance as that if the power is transferred from 50 to 7, then will be losses will be reduced. There are no losses there. That's why suppose if you select a 50 watt and you give some power, then like VP is 14.4, IP is same 6.4. Then this will be some power. This is power for the 50 watt. Then 50 watt will transfer. It will also, if some other condition, it will increase only. It will not decrease because the data sheet will be given as the 50 degrees centigrade to 25 degrees centigrade to 50 degrees centigrade. It will be 50 to 57. It will vary from 50 to 57. This is the minimum value. It will transfer more, but it will more transfer than there is no losses also here. If more transfer like a 53 watt is transfer from here to here, lower to the higher, then the remaining power is not there. That's why losses will be not there. That's why you should take a low as lower as the power is transferred. It means at a minimum power it should transfer at that power which one will be given to the pelleted devices. That's why we will take as a 50 watt of the Q. If Q max. If you take Q max as a 50 watt, then VP is 14.4 volt and IP is 6.4 ampere. And what is the RS? 20 minus 14.4 divided by 6.4. If you calculate this one, it will be I think 0.875 ohm. This resistance. If you not at this resistance, then the voltage will be increased. V maximum will be increased at the terminal of the pelleted device. That's why it will be causes of the losses. Same thing for the second questions. Following the given specification, what is the minimum temperature of the cool side when the hot side temperature is 25 degree? This is I think simple question. Hot side temperature is given as 25 degree. And at this time, the delta max, delta T is 66 degree centigrade. And what a delta T is higher to lower. Lower temperature is minus of 41 degree centigrade. This one. Okay. For the specification of a pelleted cooler shown below, what is the maximum coefficient of performance COP when hot side of the pelleted cooler is having a temperature of 27 degrees centigrade and operating at the maximum current and voltage? This is the maximum current and voltage. V max is 15.4 volt. I max is 15 ampere. Peltier cooling have a temperature of 27 degrees centigrade. 27 degrees centigrade is will here in this column. This is the Qmax. Qmax is equal to 130. 130 watt. Then what is the COP? QC by E, supply power. QC is given 130 watt. E is which one is the voltage supply, electrical equivalent. Sorry, electrical supply applied to the quality of devices. This will be 50 into 15.4. This is the COP. So 0.5627. Which of the following statement is true? As the temperature difference between the hot and cold side of the Peltier cooler increases, the voltage across the cooler decreases under the given condition of the constant current. If a current will be constant, then you know about this Peltier devices connection. This will be only resistance and a voltage supply through it. V I R S. This is the VP. Peltier device voltage. This is the IP. I is same as IP. Question option first is say that pillar cooler increases. I think temperature increases and voltage across the cooler decreases under the given condition of the constant current. If current will be constant, then this resistance also constant, voltage also constant, current is given as a constant, then Vp will be constant, will be not change because of constant current. Second is given as a temperature difference between hot and cold side of the Peltier cooler is increases, removal of heat from cold side decreases under the given condition of constant current. Same thing, but it given as the removal of the heat from cold side will be decreases. This means QC. If a temperature increases, then QC will be decreases because of the condition of the constant current. It means you should increase the current. Like if you see the data sheet, you can understand this one. That this one is a QC. This is a delta T, temperature difference between lower to higher temperature. This is the current. Suppose you fix the current like 3 ampere. 3 ampere current will be this one. This was 3 ampere at 0 temperature. Delta T is 0 and QC value is like a 27, approx 26.5, 27. Okay, if delta T increases, then this will be increases like that, but current will be constant. Then this will be QC, what will be decreases continuously in a linear position. You can see this one. If your temperature difference will be increases, then the QC will be decreases. And data sheet you can see here. That's why this option is correct. Coefficient of a performance can never be greater than 1. COP is QC divided by F electrical. If you not supply the electrical supply to the Peltier device at that time, you see something will be transferred because of the heat sink and other in ambient temperature. It will in positive value, but this will be 0. It should be greater than 0. It could be greater than 0 because if your electrical supply will be 0 if you not given the any supply. At that time, some of the temperature will be flow from air, transfer from the devices, the junction temperature. That's why this will be correct. The current through the Peltier cooler is allowed to exceed the rated current. No, any electrical devices is not allowed this one. Next question is given an aluminum heat sink in a figure shown below at a temperature of 50 degrees centigrade on a higher area surface. Anyone you can take this one is as a T1. This side you can take as a T2. This one is a higher, this one is a lower. Opposite side anything you can take like T1, T2. This will be 50 degrees centigrade. This will be 50.1 degrees centigrade. On opposite surface of same area. Area will be same. What is the power dissipation of the heat sink in watts, whose dimension is given as a 40 mm into 40 mm into 3.5 mm. 40 is the length, width and height. In this condition you can say this one is the thickness, this one is width and this one is the length. And thermal conductivity also given as the 211 of aluminum watt per Kelvin per meter. Sorry. This is the delta X. In meter you can say this one 3.5 into 10 to the power minus 3 meter. What is the area? L into B of this one is 40 mm into 40 mm. 1.6 into 10 to the power minus 3 meter square. Section 100 into 10 to the power minus 6, it will be 1.6 into 10 to the power minus 3. Q is given like 211. Per meter. Oh, sorry, this one is a K value. Conductivity of the metal aluminum. Thermal conductivity. Then what will be Q? Q is K into A area into delta T divided by delta X. In the formula you can see this one. K is given 211. Area is 1.6 into 10 to the power minus 3. Delta T 50.1 minus 50. 15.1 minus 50 degrees centigrade. It will be 0.1 divided by of delta X. Delta X is 3.5 mm 10 to the power minus 3. You can calculate Q is 10 to the power minus 3 is cancelled out. It will be 9.64 watt. For the same question, given at question number 5, what is the thermal resistance in degree centigrade per watt? No more thermal resistance will be delta T Q, but this one is the heat transfer, This one is temperature difference. No, but this is your work like that. This is the current, this T1, T2 or theta. Same thing, J1 minus T2 divided by F Q. The resistance. Temperature should compare like voltages. And this will be resistance. If you compare the electrical, this will be current. That's why our thermal resistance will be a temperature difference divided by F power transfer, the heat transfer rate. And delta T is equal to 0.1 degree centigrade. This will be Q. I have calculated already Q 9.64. This will be 0.01036 degree centigrade per watt. Or you can say this only 10.36 per milliwatt. I think this will make out. Leave this one. Next question is given as an aluminum heat sink is used for post condension cooling as shown in the figure below. What is the Reynolds number for the post condension cooling if the velocity of forced air is 10 meter per second? And viscosity also given of the air is 1.8 into 10 to power minus 5 meter square per second. This will be air viscosity. For the Reynolds number, Reynolds number is velocity, air velocity into x dimension, characteristic dimension, and viscosity. This is the air flow from here to here. This is dimension 40 mm. This is the, you can say this is the x dimension of characteristic dimension 40 mm. 3 meter. Then you can calculate Reynolds number. U is given as 10 meter per second. So 10 meter per second. This will be 40 10 to power minus 3 1.8 into 10 to power minus 5. You can calculate this one. 2 to 2.22 into 10 to power 2. There you can say this one 2 2 2, I think 5 2. Option number first. The next question is given as that the heat sink discussed in question number 7, the same heat sink. This one is length of 40 mm. Someone has been used for the forced condenser cooling. Calculate the power dissipation in air. If the temperature of the heat sink is 70 degrees centigrade and the ambient temperature of air surrounding the heat sink is 30 degrees centigrade, consider expression for the Nusselt number as n is equal to 0.664 into 10 to into or this is r to power 0.5. Don't confuse this one. I have written here 0.664 into Reynolds number 0.5 point power 0.33 power of Reynolds number less than of 5 into 10 to power 5. The second one is given for the 5 into 10 to power 5. Second is given 0.37 for the greater than 5 into 10 to power 5 into r to power 0.8 b till 0.33 for Reynolds number 5 into 10 to power 5 greater than 5 into 10 to power 5. Reynolds number decide to the flow of the nature of flow of the air or any medium temperature. If this one is the lower than this one known as the laminar flow. If this one Reynolds number is greater than 5 into 10 to power 5, this one known as turbulent flow. Laminar and turbulent flow you can see here. Laminar flow, this is all of the wave rays going in straight line, but in turbulent flow some distortion also occurs in this medium. That's why here the Reynolds number is greater than of 5 into 10 to power 5. Here is the Reynolds number of less than of 5 into 10 to power 5. For the surface, flat plate surface, it will be difference for the different surfaces like cylindrical or another thing, and tilted surface. Many of things have a different type of Reynolds number. That's why first of all you calculate the Reynolds number of this one. After that find the n value, Nusselt number. Or the Nusselt number you can say that the power is the formula k into a to Reynolds number into delta T divided by of x. I total the dimension, characteristic dimension, where this is the area where the heat is flow passing through. Reynolds number, you know, this one is the delta T, temperature difference, the characteristic dimension. This is thermal conductivity of the, is a different for the different medium. Air is different. This one is the thermal conductivity. Okay, to find the overall power Q, C, you should calculate this one. But there are different things. This is the force cooling, force convection. It means fan is here. Some of the heat you can see here. This is the case. Case temperature here is the, this is to take, this one is the part of, this is the hot part, this is the cold part. Peltier device is here, placing here. Some of the heat is flow like that, because of the Peltier devices. It will flow from cold to hot, this one like that. But by the force cooling, then some of the power, some of the heat flow in this direction also. Then there are two part. Which one is the upper side? Is the top flowing, the temperature is flowing from the top, and the second one is the from the side. Then calculate all of calculate the both, and then add this one, and you can find the final power. Then first of all calculate the this surface is the top surface, passing through top surface. In both condition, you should calculate all the thing like this one. Delta T will be not change, it will be same. Reynolds number, Nusselt number is will change because of the n is depending on the Reynolds number. Or Reynolds number depend on the flow of heat, turbulent or laminar. Then first we'll calculate the Reynolds number. Then you can find the laminar turbulent. After that you can use the formula for the Nusselt number. Then you can find Nusselt number. This will be fixed. Thermal conductivity is fixed of the air. Characteristic dimension, it will also can change. It will depending on the surface where is the flow the heat from top or side. It will depending on the dimension of type top and side. Then we start calculating from top. After that, calculate the from for the side also. This is a flat plate because of the dimension is given as a 40 mm into 40 mm into 3.5 mm. It will looks like that. It is flow here and leave from here. This is a 40 mm. This is also 40 mm. The thickness is given as 3.5 mm. This is the flat plate only. Flat plate you can say, because of this one is placed directly. Reynolds number also mentioned here, then you can use this formula. For the flat plate, first probably it will be given as a velocity u is 10 millimeter per second. It will mention in the question. It is mentioned, I think, question number 7. Yeah, 10 meter per second. This is related to the question number 7 also. That's why you can take 10 meter per second. Surface temperature is given as 70 degrees centigrade. Ambient temperature is given as 30 degrees centigrade. And what is the delta T? Delta T is 40 degrees centigrade. Here is mentioned as this one is the 70 degrees centigrade and this one is the 30 degrees centigrade. First of all, I calculate the heat flow from top. This will be Q top. Formula will be same. Area, this will be the Reynolds number divided by f x dimension, characteristic dimension. This will be delta T. Then find the area x and delta T. And what is the area of this one? This dimension is given as 40, 40 and 3.5. If you talk about the at the top of this one, at the top of this one, you can see this type of structure. I think in this is a square 40 mm and 40 mm. Thickness will not show in top of the, if you talk about the top of this one system. And what is the area of this one? Same thing, 40 mm square, 40 into 40 mm, written here. Area is 40 into 40 mm square. You calculate in meter. This will be 1.6 into 10 to power minus 3 meter square. This will mm is 1 meter is equal to 10 to power 3 mm. What is the x? X also same, because of you talk about the top, it will looks like this one. Okay. This is the top and this will be 40 mm also. X is same as 40 mm. It will be 40 into 10 to power minus 3 meter. A and x calculated. Delta T also calculated. This one will be 70 minus 30 will be 40 degrees centigrade. K is mentioned in the question already. For the air thermal conductivity, 0.026 0.026 watt per degree Kelvin per meter.
Excuse me, sir. Sir,
Oh,
for x is equal to 40 mm. How it is, sir?
this is the dimension where passing through the surface, flowing. Where is the flowing of the heat? This is heat flowing like that, na?
Yes, sir. Yeah.
If you talk about the top, this will be flowing
Oh,
like that and leave from here.
okay.
That's why this surface is the area, it's a length, dimension of this one.
Ah, that is 40 into 40.
40, no, no, this one is only 40. Dimension is only
Okay.
40.
Okay. X.
Area is this one is a 40 into 40.
Ah, area. Oh,
Uh,
dimension. Okay, sir.
this one, the area of this one is a 40 into 40, but dimension is a 40 only.
Dimension is the length.
Yeah, because of same thing you can say, you can see here, na, this one.
Ah, okay,
This
okay.
length is the x.
Okay, sir.
All of thing is there, but n is not there. To calculate the n, first of all find the Reynolds number. Then Reynolds number, this one is u x into viscosity of the air. This one is the velocity 10 meter per second. X is the 40 mm. You can say this was 10 to the power minus 3 meter. And viscosity of air is also mentioned in the question. Kinetic viscosity of the air is 1.8 into 10 to the power minus 5 meters square per second. Put the value here, 1.8 into 10 to the power minus 5. And what is the Reynolds number? This will be 0.222 into 10 to the power minus 5. 10 to the power 5. This will be goes to upper. This is 0.222. Or you can say this will be 222.222. The whole number. Then R is at 0.22 into 10 to the power 5. It will be less than of 5 into 10 to the power 5. Mentioned in the question, and also know this one is the laminar flow. That's why you can say n is for the Reynolds number less than 5 into 10 to the power 5. Then n is value of this one, the formula. When calculate n from this one, because the Reynolds number less than 5 into 10 to the power 5, 0.664 into Reynolds number of power 2.5 to this one is the viscosity, and it also mentioned here. Diffusivity 2.6 into 10 to the power minus 5. Zero 0.664 into R to power 0.5. This is viscosity divided by F diffusivity 0.33. So take a whole number, this one 2 so 52 into 0.22 to power 0.5. Viscosity 1.8 into 10 to the power minus 5 divided by F 2.6 into 10 to the power minus 5. to power 0.33. This one. Calculate the value of n from here. This only minus 5, it will cancel out. 10 power minus 5, 10 power minus 5, 1.8 divided by f 2.6. This value is 0.6923 to power 0.33. The whole value is 0.88. I can written remaining part I am written here. This whole value is 0.88. Then what is this one? 2 power 0.5.
149.07.
This will 149.
0.07.
Okay. Then calculate all of this one n. And I think this one will be prox 87 point something.
Into. Sir, overall, yeah, 87.6.
87.6. Okay. We have calculate n for this one. If n is calculated, then put the value here q top. K area Reynolds number x into delta T. K is thermal conductivity is given as 0.026 for the air. Area also calculated 0.6 into 10 to the power minus 3 meter. Reynolds number I calculated 87.6. It will be a 40 into 10 to the power minus 3. Delta T will be 40. To calculate this one, I think this will be 3.647 watt. This will be Q top. Then second one Q side. Formula will be same. K area, Reynolds number into delta T. But this dimension will be changed. Area will be changed and x can change. But we can see what type. What is this one? The same plate, but flowing from the side. Uh, Temperature is flowing from the side. You can say this one will be like
Sir, what is the answer, sir? Q top?
I think 3.647.
3.647.
Yeah.
Okay.
This will be flowing from here to here inside. This will be keep on the top of this one. This plate is keep on the top of the element. Then in the side view, this will be so like only this one. This is the top, downside is the bottom. This is the side view. You know this is the dimension is 40 mm.
into 3.5.
Yeah, this one will be this dimension will be mentioned as a 3.5 mm. Okay, this is side view. So what is the area?
40 into 3.5.
40 into 3.5 into 10 to power minus of 6 meter square. What is the dimension of x? X same thing. Length of this one will be same
40 mm.
40 mm. Then next will be I written here 40 into 10 to power minus 3 meter. We calculate this one a and x. Then calculate the Reynolds number. Reynolds number will be is the u velocity into x by of v. X will not change, velocity will not change, viscosity also not change. Then this will be I think same Reynolds number 2.22 because of the x will not change in this condition. X will be same for 40 mm. Velocity is not change, velocity is the same 10 meter per second, and this will be viscosity also same. That's why Reynolds number will be same. Then you can say Reynolds number also less than 5 into 10 power 5. In side view, this will also same Reynolds number. Then use the same formula to find the Nusselt number.
Sir, what is n, sir? N is
And Nusselt number. You can calculate the power from the calculating the Nusselt number. Na? The Nusselt number is depending on the Reynolds number, or Reynolds number depending on the flow of the thermal flow like heat flow, turbulent or laminar. Then L will N also be same because of this was the less than a 5. Same formula we can use. Use the same formula 0.664 into R with the Reynolds number 0.5. V del will be same. Then for all formula will be same. Then Nusselt number will be also same. 87.6 will not change. If the dimension will change, like talk about the cylinder and other dimension, and that condition x value will change, area will be changed, then Reynolds number also change. If the Reynolds number change and suppose Reynolds number is greater than 5 into 10 to power 5, then you should use the formula for determine the Nusselt number is the second one formula. This one. But in this condition, both condition Reynolds number will be same less than 5 into 10 power 5. Then in the both condition use the same formula of this one. If Reynolds number is same, then Nusselt number also same. Then find the power also
Q side.
Q side.
A is
Same formula K A N Nusselt number divided by of x into delta T. K is same
A,
0.026.
A is 40 into 3.5.
Area will be changed here.
Yeah, 40 into 3.5 into 10 to the power minus
Minus
6.
6. Nusselt number will be same 87.6
7.6.
into delta T will be 40. X will be same 40 into 10 to power minus 3. Then calculate the Q side. It is 0.3188 watt. This is the power. And what is the total power? Total power is Q top plus Q side. Top is 0.67 plus side is 0.3188. Then total power is 3.96, 3.98. Sorry, this one is 647. Q top is 647. This will be changed, I think. It is 6. This was 65. 965. Can match from the answer objective. This is given as a 3.96, 2.5, 250, 10. And this is the answer 3.96. The total power is 3.965. Okay. And the next question, which of the following has the lowest thermal conductivity?
Air.
Air have a lower, yes. All of after that this one with glass, then still then copper. You can note down thermal conductivity 410 for silver.
Thermal conductivity is given by K.
Yeah. 385
K.
for copper.
410 for silver. Okay.
211 for aluminum. I think previous question it will asking you given as the aluminum thermal conductivity. And 47.6 for steel. 1.05 for glass. 0.025 for thermocol. And 0.026 for air. In this condition, air is lowest. Thermocol application, I think all of you know about the bottle of a coolant bottle. All of thing is made by the, it is between the thermocol copper, and in the between this one the thermocol is placed to restrict the temperature conduction between the in the over a bottle in a water temperature and outside the ambient temperature. This will be restricted by the thermocol. Next one, which of the following has highest thermal conductivity? This one is both are same. The lowest, this one the highest. High is the copper 385. In this, because of silver is not there, not here. Sorry, that's why copper is the answer. Next question is the Peltier element is operated from a PV source. Is it drawing a 1 ampere at a 12 volt from a PV source? The Peltier element is extracting heat from an object of the rate of 20 joule per second. The object from which heat is extracted is at 15 degree centigrade, and the hot surface is at 30 degree centigrade. Then the coefficient of performance of the Peltier element is coefficient of performance. All of you know about this only Q by E. This is the heat transfer. And this one electrical power supply. The heat transfer in watt is given as 20 millijoule per second. 1 watt is same as 1 joule per second. Joule is the energy parameter. Joule and energy by temperature is a watt. Power. That's why joule per second is same as the watt. So energy per second. You can say then Q is the same as the 20 watt. Is 20. What is the electrical power? Electrical power is voltage and current. 20 into 1. Sorry, 12 into 1. So 12 watt. 20 by 12, it will be 1.67, I think. Consider Peltier cooling system where heat is needed to be removed from an object at the rate of 20 joule per second. Same Q is they given as 20 joule per second. It will be at 20 watt and transferred to the ambient, which is at the 50 degrees centigrade. The ambient temperature is 50 degrees centigrade. It is required that temperature of the hot surface of the Peltier element is 70 degrees centigrade. Surface temperature, you can say this will be 70 degrees centigrade. What should be the thermal resistance from the hot surface to the Peltier element to the ambient? It means or theta is from surface to ambient, or is known as T surface minus T ambient, delta T divided by F Q. Delta T is 20 divided by F 20 watt. It will be I think 1 degree. You can say Kelvin, degree Kelvin per watt or 1 degree centigrade per watt, both are same. Because of if you use this one Kelvin, you can convert in this one also Kelvin, then add simply plus 273, add here also 273. Then if you subtract this one Ta minus Ts, then 273 will be cancelled out. Then the delta T will be same as in degree centigrade or in degree Kelvin. You can both are same. That's why this will be the 1 degree Kelvin per watt. Sorry.
Sir, excuse me, sir.
Yeah.
Sir, how to find, so in next question, sir, how to find out duty cycle, sir, if voltage is given and temperature is given?
Which one question?
No, actually, I'm asking this doubt actually. Yeah. In the problem, it is given that voltage is given
Yeah.
and temperature is also given. We need to find the duty cycle, sir, in order to vary the
Yeah, you can calculate a
voltage.
VP and IP na. If
VP and IP. Yeah.
if you calculate the VP, then you can say that if any converter is there, then
Uh,
VP is some power. A buck converter is a DBS supply voltage,
oh,
or
okay.
some other converter is a buck boost converter is D into 1 minus T like that.
Okay.
No, first one calculate the VP because a
Okay.
Peltier device is connected like that na.
Hmm.
Yeah, this one is no, not this one. I don't know, but this one
Yeah.
is there. The DC converter.
Yes, sir.
This is duty cycle. This is the
Ah.
VP and IP.
Yes, sir.
VP IP calculated by the Q transfer of
Oh,
power.
okay.
From where you can calculate VP. Q max. I think this will be
VP.
also given in
Yeah.
the data sheet.
Yeah. Q is the temperature. Q is
Power.
power.
Yeah.
Power is yeah. That I think I will check, sir, once.
Okay. This one DC converter. Then you can calculate from this one. This one is the converter supply some voltage. This
That
one
is
the
the
input. This one the output
input.
voltage. You can calculate duty cycle.
Okay. Thank you, sir.
Okay. This one okay. Next question: the heat transfer process through solids is called conduction. I think all of you know. In solid is a conduction,
Yeah,
convention,
conduction.
and convention is in the air medium or liquid, like that. This is the no medium, any medium. Mass transport, it means some of what fluid is transferred from one place to another place to cool this one, like a AC, and some of the transformer have a water cooling to provide some water surface to the around the transformer, a large transformer to cool the transformer. Some there, this will also mass transfer because of the water is flow from one place to another place to transfer the heat one place to another. Question number 14. In a convective Peltier cooling system, an air blower is used to produce an air speed of 5 milli per second over the hot surface of the square shaped Peltier element. The square shape, same thing. You can calculate area. All of side is 3 centimeter. And what's the area? 3 into 3 into 10 to power minus of 100. Sorry, 2 minus 9 into 10 to power minus 2 meter square. X is same as 3 centimeter. It will be 3 into 10 to power. This is minus 4, I think. Sorry, because of 100 centimeter in 1 meter. This will be minus 2. This will be meter. This will be meter square. Then what is the Reynolds number? Reynolds number, you know, U
X.
X in V. U is given as meter 5 meter per second. X is 3 into 10 to power minus 2 meter. Which is the viscosity of air? Viscosity of air is the constant value 1.8 into 10 to power of minus 5 meter square per second. So 1.8 into 10 to power minus 5, and calculate the Reynolds number. Right, and it will be 8333.33. The emittance of polished aluminum is more than wood. Can written as emittance is symbol of A is 0.8 for anodized aluminum, 0.095 polished aluminum, 180 rough surface aluminum, 0.33 for tungsten at 1500 degrees centigrade. This one polished copper, 0.9 is wood. Emittance related to the radiation, and another is related to the convention is like a thermal coefficient. This is emittance by the radiation. How much energy will be transferred from per unit area, per second per unit area. Then what is the minimum? It is the emittance of polished aluminum. Polished aluminum is 0.95. More than the anodized aluminum? No. And anodized aluminum is zero point 0.8. More than glass? This is not also because of more than the wood. No, wood is zero point 0.9. And more than the polished copper? Polished copper is 0.07. You can say this one is the lowest, more than copper, polished copper. Polished copper is 0.07, but polished aluminum is 0.095. Glass is higher than this one because of the wood is the very high, and glass also high. In a heat sink, the heat is transferred from the surface of the heat sink to the ambient air predominantly by the process of.
Sir, last question answer is what, sir?
It's more than
It's more than polished copper, huh?
yeah, yeah.
And more than ionized is also not there. Okay. Okay, thank you, sir.
In a heat sink, the heat is transferred from the surface of the heat sink to the ambient air predominantly by the process of convection. In air, the heat is transferred from convection method. Conduction for the solid. Mass transfer is another method. None of the three is given. Convection is the method to transfer the air, transfer heat from air. And radiation is a no medium. However, no any medium, then no boundaries there for the radiation. Nussel number is a fluid flow measure, dimensionless quantity, characteristic dimension, thermal impedance. No, thermal resistance is not there. Fluid flow measure, or is formula is
You
this is not this one is Nussel number. Any formula if you take this one 37 into Reynolds number 0.8 V. This is the same dimension, will be cancel out. Reynolds number also dimensionless, and all of thing is the dimensionless. Sorry, this is the dimensionless quantity. Natural number. R is the also dimensionless. Next one, the heat transfer process without any medium. The radiation without any medium. An aluminium slab is having an area of a cross section of 1 meter square. Area is given 1 meter square, and thickness is delta x. You can say like thickness 10 mm, 10 mm into 10 to power minus of 3 meter. The heat flow normal to the surface area. Normal to the surface area, it means the heat flow from top. The thermal resistance of the slab. Thermal conductivity of aluminum is given. The thermal resistance. Thermal resistance is known. R theta is a delta x divided by of k into a. Thermal conductivity into area. Okay, R theta can calculate in by the two method, delta E by Q. This one is the not given. This is the given, and we can calculate from here. Delta x is 10 into 10 to power minus 3. This will be 211 into 1, because the area is 1 meter square, and this will be the 4.74 into 10 to power minus 5 degree Kelvin per watt. 4.74 into 10 to power minus 5, and this one is the answer. Okay. Next one is a slab made of glass, have an area, same area, 1 mm square. It means 1 into 10 to power minus of 6 meter square. Thickness 5 mm, delta x is 5 mm, is 5 into 10 to power minus 3 mm, 3 meter. The heat is same thing, thermal resistance is also or theta, delta x divided by f, thermal conductivity into area. Thermal conductivity is given of the for the glass is 1.05 watt per degree Kelvin per meter. Delta x is given 5 into 10 to power minus 3. This only 1.05. This is a 5. Area is 1 into 10 to power minus 6. I think this problem m not mm square. This is a meter. I think if you take a mm, this will be very less quantity, high quantity, but there is a very less quantity in this. This one will be m square, 1 meter square area. Then this will be the 0 4.7619 divided by 5 from 1.05, then this will be answer 10 to 10 to the power minus 3. Or theta is 0.00476619 degree Kelvin per watt. And this is the first option. I think all of question is completed. Okay, everyone, I want to stop here.
Thank you, sir.
Okay, thanks you all.